Today I'm going to show how to wind a simple pancake coil. And I have a pretty simple jig here, just for flat spiral coils. It's a block of acrylic, and there are a few things that can rotate freely. We have, of course, a spool of wire, and there's another section for interleave material. This is just a roll of paper. And over here we have the actual jig that the coil is wound on as it's turning. So the paper, in this example, you can use any paper, but this is used for drywall or sheetrock. It's kind of a 2-inch wide paper, about 0.8 of an inch thick. It's really absorbent for the insulation, so it works good, and it comes in large rolls, so you don't have to continuously change lengths. Another option for lower frequency coils, you can also use like a cash register paper, and this is only about 1/1000 of an inch thick, and this also comes in different widths. And for flat coils where you need a lot more wire, this paper doesn't consume a lot of space, so you get a much tighter and compact coil. The disadvantage with these, you may need 5 or 10 rolls to make a coil, but they come in packs anyway for office use. So on the jig there's like a little insulator that I put a piece of Teflon on with a small hole in it, and this is just used as a wire guide. Now for these relatively coarse pancakes, using the study electrical discharges, I'm using like a 29 gauge wire here, and by feeding the wire through there, you have just a little guide to keep the coil sort of in the same plane. So I can start off. I have a little groove machine. There's I'm using sort of a hexagonal piece of plastic, and this groove has a cone-shaped hole and a piece of a threaded bolt in the top with also a plastic cone, and when you tighten that, it actually expands the size of this hexagon. And what that does, it puts tension on it, and then when you're done winding the coil, you can just loosen this nut and it shrinks a little bit so you can pop the coil off. Otherwise, if you wind it with too much tension, and you kind of have to fight with it to get the coil off, and it's a pretty loose coil because it's just paper and wire in the end. There's a hole, of course, in the center of this disc, in the center of this insulator, and there's also a small pin that's offset, and there's a second hole, maybe a 1/2 inch over. And what that does is it simply keeps this rigid with the insulator, so that you can spin it around and not have the insulator spinning free. So it helps to wind a few layers of paper first, just to establish a tight just sort of have a tight core on there. And as the wire comes over, I like to have some tape here. Just put just a small amount of tape just to secure the wire, and then I normally just tie it to something. You need a couple inches of wire just to be able to terminate the coil, and if it's not long enough, you can always pull some out when it's done being wound. But that's just for your inner connections. And it's real simple as you begin turning it. You can see that the interleave and the wire is wound simultaneously. Now, you'll note that I have this set up so that the wire is a little bit above center. You can wind it anywhere you want on the bobbin, but in the case of coils that are normally sitting flat like on a box, you can always cast wax higher in the coil. A lot of times the problem is the coil should be a certain height off the box so that you don't have the wooden box or the ground plane interfering with things. It sometimes helps to give a little bit of extra space in there just to account for that. Now I'm going to be putting this coil in one of the Kinraid looking molds. So there again I'm going to have this insulator like this on top, and plenty of wax on the top. The bottom I'm a little concerned of, so I'm just leaving a little bit more than an inch of space in there. Now this is much simpler than the multi-layered coils, such as the ones in the Kinraid coil itself. And that you can never do this continuous insulation. Those you have to wind 10 or 15 or 20 layers, turns per layer, and manually insert insulation each time, or the interleaves. And in that case, as the coil grows, you have to kind of calculate how long the interleave should be to make it consistent, and it's much more time consuming. And because there's so many more turns of wire on it, it gets pretty tedious. You have to wind it, and a lot of times, like in the Quest for Kinraid video that we did, you can see I actually dipped the interleave material in hot wax to sort of glue it to the windings as you're doing it. Otherwise, you'll wind the coil, and a third of the way through, it'll all start unraveling on you, and that's a nightmare, because then you end up throwing away wire and losing a lot of time. The multi-layered coils, they may take a few hours to wind. We'll probably show winding one of those too, just for reference. But these flat spirals are pretty simple, and this is pretty much the extent of it. And of course this could be motorized and made simpler. We have a motor driven winder, but I found it's more convenient to wind these horizontal for the flat spirals, because if you wind them vertically, sometimes the weight of the whole assembly starts to pull down, and you end up with kind of an egg-shaped coil in the end, which doesn't really affect things that much, but this is a little bit simpler and easier to manage. Gravity isn't as much of an enemy with this setup as with the others. And by doing it by hand, you kind of have a little bit of control over everything. These don't have to be exact for them to work. One thing you have to be careful of is to sort of always pull it with the same tension. If things get loose, what will happen, you'll have the coil done, and then you may have windings that fall down to the bottom just because there's not enough tension on maybe one section of the coil, and that's not good. They'll short out in an instant. We're about a 4 to 5 inch diameter coil right now. You can see there's very little wire in these particular coils. When this is done, we'll have about roughly 250 feet of wire total, and it's going to be around 200 turns. And for making large sparks, you would want a different setup. Many more turns of wire. It is possible, though. We've had a pair of these coils that were making a 12 to 14 inch discharge. You have to put a fairly excessive amount of power through them to get that. So these are very efficient for studying electric phenomena, like the phantom streams, but they're in that case you can run them with only 15, 20, 30 watts of power, and they make a real impressive display. If you want sparks, you're going to need to use thinner wire and a thinner paper, or the same wire and just many turns per layer. With a 9-inch coil of maybe 700 to 1,000 turns of wire, you can expect a 12-inch discharge pretty easy. At 20 watts of power with these smaller coils, you normally don't get much more than a 3 to 4 inch spark. But you get this beautiful halo effect all around, which is most interesting. It's also a very efficient coil to produce ozone. If you put two plates on, if you have a bipolar arrangement, you have like 6-inch plates. You can separate them 6 to 8 inches apart, like a big capacitor, and all of the air will ionize between them. Makes a really beautiful display. And that's something classic Tesla was doing in his lectures to show artificial lighting. Not the most practical lighting, but well, you know, Tesla wasn't always looking for practical commercial things. Just showing, you know, the wide variety of things you can do with high frequency. Now, keeping tension on there, I'm going to see where we're at so far. Alright, we're about 7.5 inches. This particular coil I want to go up to about 9 inches. There's also a little Sharpie mark on here if when you're actually winding, if you're counting the layers and trying to be very precise, it helps to have some sort of reference point to be able to count as you go. Because obviously doing this to you is kind of confusing. Eight and a half inches almost. Roughly 8 and 7/8 inches. Okay, that's good. Now we're at 9 inches. So I've got some electrical tape. Just try and secure things a little bit so they don't all unravel. Also helps to secure the inner leaf so that also doesn't loosen up on you. And here's a 9-inch coil. Now, the next part gets a little tricky. It's time to insulate this coil. As it is now, it's a little too flimsy to actually handle it. You can put it in a box, but it helps to actually precast these in wax before you cast them in the final product. And because wax will stick to itself, it doesn't make any issues. If it was certain resins, there might have problems because of certain resins, if you cast them on top of themselves, they may or may not stick well. Wax, fortunately, does stick well, and then the other wax will just sort of melt and it'll all form together as long as it's hot enough. The other thing, if you cast it precast it in wax, you could always put it in the form and heat it up until all of the wax, the new and the old, are all liquid. And that helps even further to get out all the air. So right now, it's time to put this in a container and cast it. So we have here a simple silicone pan. This is used for baking. They were popular a few years ago in the cooking stores, but I think anyone that's ever used them hates them, because if you're trying to make a cake, you fill it full of batter and then you go to pick it up and it goes whoop, and all the batter goes all over the floor. So they're kind of redundant. You always need to put them in another pan. So for cooking, they didn't really catch on very well. Though they are non-stick, they can withstand high temperatures. They're getting harder to find because no one wants them. But for coils, they're perfect, because one of the problems when you cast these in wax is it's hard to get them out of a container. Depending on what composition wax you use, it may grow or shrink a little, or it might be a gooier wax, like a container wax, where you can't handle it very easy, where you start trying to pull on it and it just, you get your fingers stuck in it and it makes a mess. So to get this coil out of here, I mentioned that little tensioning device. I'm going to loosen that. That'll make the hex a little bit smaller. And I've got a sort of a spring-loaded deal on here to hold down the form. And this actually also, it puts tension on the whole assembly. So if it was really loose and free spinning, you'd have problems with tension as you pause and go around. The coil would start to loosen up. But because there's a bit of resistance there as you're winding it, it kind of keeps everything tight and formed well together. So this will lift up. And you can see on the bottom, I mentioned that offset pin. That's what keeps this guy locked in the position. Now for the center here, all I have to do is lift up on this and it'll come right out. Now before, there was enough tension that it would push hard against the inside of the coil, but because of that little split in there, whenever you tighten this, it acts like a collet and expands it. So now we have the coil. Right now it's facing up. Can carefully flip it over here. And this is where you run into problems if the coil isn't wound with enough tension, because as you're moving it, those windings would be falling all over the place. So simply invert the silicone pan on the top. And whoop, I didn't use my measuring stick well enough. I actually put a little bit too much wire on here. And the diameter is a little bit too big. So to fix that, I'll have to take off a few layers. But I'll do that, we'll get it in the pan, and it'll be ready to cast. So I've corrected my little mistake. I had to remove maybe 5 or 6 layers of wire. I hate doing that because anytime you loosen the tension on stuff, things can start to have slack. But if it does happen, you have to just constantly apply attention to it while you're doing it. So right now, we're at the right diameter, and simply carefully put the silicone pan on top, flip it over, and here's our finished pancake coil. Now, to precast this, I'm going to bring it outside and fire up the induction stove with some wax. And by having it partially solidified in the wax, it'll make the casting process easier when it's put into a mold. Speaking of pancake coils, we'll just have a look around. I mean, most people visit the site know about the Kinraid coil. Of course, in the cabinets we have the early prototypes. that Kinraid made in developing this device. We've shown these on other videos. On the top shelf we have some very historic pancake coils from Bill Wysock that continue over here. And these were coils from Kenneth Strickfaden's collection. Of course, we all know Harry Goldman. He wrote the biography on Ken. Ken's famous for doing over 100 films with Tesla coils. All the live effects from the Frankenstein films were all the product of Ken's creativity and imagination. Kinraid, neither Kinraid or Tesla was the first to start experimenting with flat coils. We know that in Ireland, Nicholas Callan made a great induction coil that used 3 large pancake coils, and he began this in the 1830s. The real pioneer of generating very high voltages was Edward Samuel Ritchie, and this is the 12th coil he made in 1857. This top section contains many flat spirals, and this became the standard of how to wind induction coils. At a time when Ruhmkorff was lucky to make a 1-inch spark, Ritchie made a 15-inch spark. And this particular coil here is rated for a 12-inch spark. And it still produces about a 4-inch spark. We need a glass tube to insulate between the primary and secondary windings here. But historically a very important coil. He developed this flat spiral technique. Poggendorff kind of hinted around that if you sectionalize coils you could insulate them better, but Ritchie's the one that really took off with it and come up with this winding that's sort of perpendicular to the core of the coil for the secondary. Ruhmkorff literally stole the design, bought one of Ritchie's coils, dissected it, and because Americans weren't given much credit in especially 1800s, at least in Europe size, Ruhmkorff's the one that got credit in most history books with the induction coil. And he did make some great improvements, but the real spark, or the real improvements in how they operated, and the first person to really get big sparks was definitely Ritchie. Unfortunately, he, after Ruhmkorff kind of took off with his design and Ritchie was left in the dust, he went on to develop liquid-filled compasses and became a very successful career in that later. But here's the coil. We're ready to go insulate it, pre-insulate it outside. This is a coil form we're working on to contain the coil, and this is made out of polyester resin, basically Bondo. And here you see a coil that already done. Lift it up. You can see that the coil is cast on the inside here. And this coil, before I put it in and cast wax all around, it was pre-cast first. It's very heavy. And that's what we're going to do now with this. So coming over to the workshop, messy workshop, first thing you need is a clean workbench. That's not going to happen anytime soon. It's a very flat workbench. I have a piece of granite on top, and it's actually made very level. I've shimmed the sides. So when I put wax in something like this, I don't have it overflowing on one end and a half-inch empty on the other end. So it helps. You need a very level surface. I've often thought about making a gimbal or something where we can just do it anywhere. But this kind of messy setup here, this is an induction stove, typically used in catering and restaurants. You never want to heat wax directly on the stove because you have a problem. Wax is like oil. It has a smoke point, and if you exceed the temperature of the wax, it'll literally burst into flames. And we had that happen with a friend of ours, a violin maker, who is making his own varnish using Venetian turpentine and different things mixed together, and kind of a classic electrophorus mixture that the Tesla crowd would know of. And he just went in the house a minute while he was melting it, and he come back in and half of his garage was on fire. So you have to be real careful. With these induction stoves, I like it because you can regulate the temperature really accurate. It's sort of graduated, starting at 120 degrees and going up. So you can start off low, let it melt. The other option is to have a double boiler. Doing this in the house isn't recommended. Anyone that's married will probably soon be divorced because there's invariably always spilled stuff or something dripped somewhere. And when you get wax on, especially on kitchen stove, it doesn't come off very well. Wax, it's important. No, it's extremely dangerous. I mean, it's something you don't think. You see candles and things, you kind of casually think about it, but this wax, if you're burned by it, it's the same as being burned by hot oil. The difference is the wax sticks to your skin and you can't get it off. The burns, even very small burns from wax can turn severe just because of the fact that the heat gets trapped inside. You really need to be very careful with working with hot wax or resins of any kind. They're extremely dangerous. And I've had a few minor accidents, and behind me is the swimming pool. I've had my arm in the swimming pool instantly before, just getting a couple inches of wax on my arm, and by the time you get it off, you have severe burns and you're in agony for at least a week. So take a lot of care with wax. So you'll see it's just starting to melt inside. We're going to leave this alone for a while at low temperature until it's liquid, then we're going to cast it in here. You can see now our wax is melted, and this is a paraffin wax mixture. This here in my hand is beeswax. This is the ideal material to use. Beeswax and rosin was traditional, and that as an insulation it was actually used back since the 1700s, even for static machines, and even as a type of cement and gluing parts together, electrical parts. The problem, beeswax is up over $15 a pound right now. To make one of these coils with beeswax and rosin, especially if it's in one of the molds, you're looking at $100 in materials. Even paraffin wax now, a 10-pound slab, is up to around $35 here. It's really gone up a lot in price. The other option is saving candles, or looking for them. I've had a few people send me candles over the years, which I'm grateful for, because wax is one of those things you can recycle as long as it's clean. So here's our form. Move it a little bit closer. I prefer to ladle this wax into the coil because anytime you pick up this pan, you risk spilling it and really hurting yourself. So first thing you'll notice, all the air bubbles. This wax, it takes time to absorb into the paper, and what you end up with is a lot of air bubbles. Of course, you don't want those in the final coil, but they dissipate after a while. Another option you can do is to soak the paper first in like an oil. And of course it gets a lot messier in the winding process when you do that. But by having the paper pre-soaked, you get less of this bubbling. That's especially useful, well, like in the Quest for Kinraid video we did before, we showed dipping the paper in wax first and actually sort of precasting it as you go. Especially for the multi-layered coils where any air bubbles would be a real problem. That's kind of the recommended route. In these flat spirals without as many turns, you still want to try and keep as much air out as possible, but it's not as critical as with the other coils. When you have multiple turn per layer coils, you have to not only worry about layer to layer, you have to worry about the windings in each individual layer. This thick paper works a lot better than the thin because it's more absorbent. When you have the thinner paper, a lot of times if you cast it like this, you can demold it later and you'll find sections of the paper that didn't get coated with wax. And that's simply because this paper acts more like a wick than the thinner paper. There again, for those thinner inner leaves, it helps to pre-soak them. But to do a video, that's a lot messier because then you have dripping oil, and you can imagine. The other reason I removed some of the windings, you can see a kind of gap on the side of this container. It helps to have that little bit of void because it lets the oil flow around to the bottom of the coil easier. If it's all compressed inside the container, you have to sort of wait for the wax to descend to the bottom. This way it kind of keeps it flowing all around. Well, it's good to note now that I'm getting low on oil, I'm actually going to turn off the stove because you have a danger of overheating it. Low on wax, rather. Sometimes you get a small impurity in there you have to take out. But right now, that's actually a piece of electrical tape on the end of there that melted. So the best thing, once you get a bit of wax in there, leave it bubble and do its thing, and in a few minutes time it should be clear and liquid on top. Now you can see as it's cooling a bit, the air bubbles are starting to subside, and I'm going to start working on the mold a little bit more. Now, one of the problems, you need a receptacle on the top of the coil for whatever your discharge ball is going to be. I normally use spent cartridges or new brass casings for cartridges. This is a 30-06. I've used Colt 45s before to work well. But I mean, just machining the ends off, you end up with a flat bottom receptacle, and that makes a nice socket for a ball terminal or a little toroid or discharge post, whatever you're going to put on top of the coil. So to prepare our mold, we have to drill a hole in the top. Now we have a hole in the coil form, and I can begin to epoxy this little receptacle on the top, and that's what's going to take the center wire to our coil. I've set up a small fan here, and the coil is slowly cooling. And this process will probably take a few hours before it's fully ready. Now check on the coil. You see that the wax is cold. And it's just a matter of demolding it from the silicone. Nice thing about these silicone pans is that you can do this in just a few seconds. And you see, here's the final coil. Now, this can either be placed in a box, you can make a center post for it, and then wind a primary, cast the wax all the way around. Or in this case, I'm gonna put it in the second mold. But it's pretty much ready to go. I've managed to fix the center wire to the post we drilled earlier, and now it's just a matter of recasting the whole container with wax. When everything's said and done, you have a durable pancake coil. In this case, it's in sort of a fake hard rubber mold, mimicking Kinraid's. But you can see the wax hardened in the bottom. The coil's secure. The primary winding can be put on the outside, either cylindrical winding or a flat ribbon and another flat spiral. And the socket's ready on top. And the ground wire, or low voltage side of the pancake, is just terminating out of the side. So typically that's just grounded to the innermost turn of the primary coil. But you could connect it to a separate earth ground if you wanted. But that's how you make a coil, basically. It's one of the simpler forms of pancake coils. There's limited application. In this case, it's mainly studying electrical discharges. But of course, if you were to use thinner paper, more wire, you can have a coil that makes a 12-inch spark or more. And of course, the concept can be continued in large coils. We've made coils over 2 foot in diameter that made sparks 3 foot long. Any of these type of experiments you can do, and this is the beginning. This is the simplest sort of pancake coil you can make. As a final note, talking about pancake coils, because it's such an obscure topic from at least a modern Tesla perspective, there are always idiots, for lack of a better word, that tend to take this technology and promote things such as free energy and other pseudoscience nonsense, and they try to couple it to Tesla's name and legacy. And for us serious Tesla experimenters, there's nothing more despisable than that. And what's discouraging now, I'm even seeing in educated countries like Russia, Russian territories, even in Tesla's homeland of Serbia and Germany, places you think people are more educated than even the U.S. I mean, it sounds bad to say, but we do know the education levels in these countries are very high. And yet still there are people promoting this free energy nonsense everywhere you go. It's really disappointing. It has to stop. At some point, people have to say, look, Tesla, he did such amazing work. There's no need to embellish or make up nonsense. So much has gone on since the 40s in that direction, and it does nothing more than give Tesla a bad name, and as well as all the other pioneers from that time period. It's really disappointing and disgusting, actually, because most Tesla conferences now you go to, and there's nothing but people speaking nonsense, really, a lot of the time. So, as a community, Tesla community, the best thing we could do is just reject that as a whole. And the good news, there's a lot of new people getting introduced to Tesla because of TV shows and different programs, and they're looking objectively with an open mind towards the real history. And as long as we can encourage that new crowd to beware of the nonsense. I mean, if something's too good to be true, normally it is. Now, Tesla was a brilliant inventor. He is responsible for many, many improvements we have in the 20th century. But there's so much baloney that's been written about him that's just nonsense. People trying to get 15 minutes of fame. And what happens, the stories get regurgitated over and over and over again. And it's just ridiculous. So, in the case of Pancake Coils, it'd be very easy for someone to promote this sort of nonsense just because the average, even the high voltage people don't normally work with these type of coils. If I see anyone doing that, I'll try my best to call them bluff. And I've done it before, and I'm not embarrassed to do this, because in the end you're only protecting Tesla's name and the other real pioneers that were trying to do something. These coils are interesting. You can operate them. You can see all sorts of neat effects. There's genuine unexplored territories with them as far as how electrical discharges form in the air and corresponding similarities to, say, lightning in the upper atmosphere. A lot of very interesting effects. There's no need for baloney. There's no need for nonsense. So, to everyone in the Tesla community, please stop this. I mean, I think for the most sincere of us in the crowd, we couldn't stand it all along. But a lot of people sort of turn a blind eye or look the other way. Not wanting to offend people, but that hasn't worked in the last few years. It's time to speak up. Offend the people that are doing nothing, because if you look close, most of these devices they're promoting are dead ends. All of them are, actually. And you need only to show up to a Tesla conference and see some of this absurdity up close to realize how bad it really is. So Tesla has a great legacy. It's amazing history on its own. There's no need for nonsense. And I hope people will take that to heart and actually kind of help to stop promoting this sort of thing. And even those who don't promote it, if you're not speaking up against it, then you're not really helping the cause at all.